Hi everyone. Before we learn about the concept of work mathematically, we need to know the product, one of the vector product, which is scalar product. Between vector multiplication of vector, there are two kinds of product possible. One is scalar product, the other one is cross product. The scalar product is related to the definition of work. Between two vectors, scalar product is defined as the magnitude of two vectors multiply, and then cosine angle between the two vectors. If you have coordinate representation of the vectors, then you can easily prove that the work is defined as the inner product between force and displacement. If an object is moved by a displacement delta r while some force F is acting on that object, then the work done by the force on an object is the inner product between the force and the displacement. The sign of the work is determined by the cosine theta, angle between the force and the displacement. For example, work can be even negative. Work can be positive only when the cosine theta is positive, meaning theta angle between the force and the moving direction, displacement of the object, is 0 to less than 9 degrees. When you stretch the spring, how much work you should do? We know by Hooke's law, the restoring force is proportional to the displacement. So to stretch the spring, you need to do some work by applying this force, cancel the restoring force. Work done by you is when from x equals 0 to x, you basically find this area, which actually, even if you don't have to do this integration. This force times distance, the area of this here will be 1/2 kx squared. Force here is kx, here is x. This times this, kx squared over 2. This is the area, which is work done. That's stretching us. In the most general case, we assume that force is parallel to displacement vector. But in general, displacement and force doesn't have to be parallel. Their direction can be different. In that case, we need to do this dot product and then integrate. Very, very complicated. For a simple case, actually, is this. Here, force is downward, vertically downward, but this object will move along the slope. Displacement and the force has different direction. But then, you don't have to do this complicated integration. Very simple. What really matters is the force in the direction of this displacement, or the displacement in the direction of the force. Whichever you use, you will find that when this object to move to the down here position by a height h, the work done by this gravitational force will be mg. And then you can distinguish between work and net work. The work you do in moving an object involves only the force you apply. For example, when you lift an object at a constant speed, you do some work. Why? Because, for example, if this object moves upward because there's a force, mg, right? Downward, which is gravitational force, you need to apply force upward, which is mg, to cancel this gravitational force, to move the object upward. Then what is the work done by you on this object? If it moves by h, this is mgh, you do work mg. Then, on this object, what is the work done by gravitational force? Gravitational force is downward, displacement is upward, so minus mgh is the work done by gravitational force, which is negative work. And net work, if I ask you what is the net work done on that object by the net force, then it's 0. Why? Net force on the object was 0. The force that you push upward and the gravitational force downward on the object cancel each other. The net force was 0, even if the object moves upward by h, displacement h, because net force was 0, net work is 0. Total work is the net work. So total work, mgh plus minus mgh is 0. Okay. If I apply Newton's second law to the net work done on an object, net work is, by definition, is the work done by net force. And net force is equal to ma. Let's assume mass doesn't change here. Then, here, by definition, acceleration is dv dt, and if you switch this to dx dt is velocity. So, net work done, if you evaluate this from v1 to v2, initial velocity to final velocity, then it's 1/2 mv squared difference. So, if we define this 1/2 mv squared as some energy, kinetic energy, then we can say that net work done on an object is equal to kinetic energy increase, kinetic energy change in the object. This is actually, you already know this equation. This is ma times delta x. delta x is this displacement. We learned in chapter 2 that if you divide each side by 1/2 m, then this equation is nothing but v2 square minus v1 square is equal to 2a delta x. What is this equation? This is the one that we derived when a is constant acceleration motion, right, by removing t. And that's actually work energy theorem. We will solve some problems related to this work energy theorem. Very, very important problem. The theorem. You can solve many problems, and also we will keep applying this theorem in later chapters also. Very important. Power is defined as rate at which work is done, or at which the rate at which the energy is used or produced. By definition, power is work, delta work, or delta energy divided by delta t, every power. So instantaneous power is time derivative of work, okay, or energy, dW dt. Unit of power is watt. 1 watt is basically 1 joule per second. If you know power, you can find out what is the opposite to derivative. It's integration. So once you know power, you can find work by integrating power with respect to time. Okay? In this chapter, we learned work, concept of work,